take energy. Where could you get the energy to do it? One place, of course, is from your own muscles. You could supply the energy to push the log. Or someone else could supply the energy. Then the energy would come from someone else's muscles. Or you could use a machine, like this bulldozer. Then you'd be getting the energy from gasoline. Or you could even use an electric motor. Then the energy to move the log would come from electricity. But let's say you didn't have a friend to help you. And let's say, at least for now, that there weren't any machines around that use gasoline or electricity. Then where could you get the energy to move the log? You could still use your muscles, of course, or the muscles of other animals. But are there still other things around you that might have energy that you could use? Well, here's a small rock. Suppose you wanted to crack it in two. That would take energy. Where could that energy come from? Suppose this happens. The energy to break the rock in two came from the large rock that fell. But wait a minute. There is energy in a rock? How can that be? It doesn't look like there's energy in the rock now. But there was when it fell. What's going on here? The answer is that when the rock was falling, it had a special kind of energy called kinetic energy. All that really means is that it was moving. And because it had kinetic energy, it was able to apply a force to something else by falling on it.
Okay, so we're going for a ride around the pyramids. The Great Pyramid was the tallest man-made structure for nearly 4,000 years, only surpassed by a large margin by the Eiffel Tower in 1889.
147 meters high. You are interested by climbing?
Yeah, let's climb it.
But it is not free.
How much? What makes the pyramids even more impressive is that these structures were built over 4,500 years ago. When Egyptians didn't have wheels or steel, the only metal available was copper and copper alloys. It took about 2 million stones to build that pyramid. Well, I call them stones, giant rocks. Somewhere between 1.5 and 3 tons each. The pyramids took about 20 to 30 years to make. It's a long time, but if you think about the number of stones, a couple million stones in every pyramid, you'd have to be laying a stone roughly once every 3 minutes. If you consider a regular workday like a 10-hour, 12-hour workday.
Nobody knows how they build it. It's still secret. But a lot of people, they try to do the best to give you some information about how they did it. But we must say it's secret. They did, and they take the secret with them. Nobody knows.
No plans survived to show us how the pyramids were built. So perhaps it's not surprising that this is the subject of countless conspiracy theories involving aliens, time travel, or lost technologies. But there is a less far-fetched myth, which has become widely accepted, that the pyramids were built by slaves. But recent discoveries suggest the pyramid builders were not slaves at all. They were skilled workers. Well-preserved tombs near the pyramids suggest that their hard labor and sacrifice were rewarded. If these workers had been slaves, they would not have received such honorable burials. But how did they actually manage to build the pyramids? One of the things I find really interesting is that the Egyptians didn't know about wheels, so they didn't really even use rollers as far as we can tell. I mean, these rocks would have been carted across the desert on sleds. There's a famous diagram of this giant statue being pulled by 172 men, and that statue would have weighed somewhere on the order of 68 tons or something. This would normally create a lot of friction, but the sand was wetted in front of the sled. Experiments show this would reduce the pulling force required by half. The internal stones of this pyramid are all limestone, which is a bit softer and easier to work. You can imagine them working it with those copper chisels that they had. Some of these blocks may have been actually sawed through using copper saws. Now you wouldn't think that copper could really cut rock, but if you put an abrasive in there like a sand, you could actually wear away the stone. Probably be a very difficult and labor-intensive job. Something that you don't really think about is that when you build a pyramid, you need to build it on level ground. You can actually see there how they had to level out that ground. Well, it's speculated that when the Nile flooded, they put the floodwater into a channel and see where the high parts were. So the inside was made of this limestone. The outside of this pyramid was actually made of granite. Much harder stone. I'm at the granite quarry in Aswan, where they would have quarried the stones that were used in the pyramids at Giza. Now that is an incredible feat because this is nearly 1,000 kilometers away from Giza. And when the Nile flooded, water would come right through here so that they could move all the stones quarried here, this granite. They could move this back up to Giza and use it on the pyramids. These would have had to have been floated down on rafts. Now, quarrying this would have been really hard. Granite is one of the hardest rocks because it contains quartz. And quartz on the hardness scale is about a 7, where diamond is a 10. So how would you dig a massive trench like that? Basically, the technique was just to smash the dolerite rock into the granite over and over and over again. They would make about 5 millimeters progress per hour. So there is no clear account of how the pyramids were actually built, but the best guess is that ramps were used. And in fact, some ramps have been found on incomplete pyramids, but you can't build just a straight ramp, a long straight ramp, and keep putting the rocks up. I mean, the problem with that is the ramp actually ends up taking up more material than the pyramid itself. I think a ramp which sort of wraps around the pyramids is probably the most likely thing. The top third of the height of the pyramid actually only accounts for about 4% of all the material in the pyramid. That's why it's suspected that levers were actually used to finish off the pyramid, to do the top levels. Now the pyramids have clearly weathered, but in the past they would have been a brighter white because they would have used a white limestone to cover the whole face of that pyramid. And then the very top may have been covered with electrum, which is a mixture of gold and silver. So if you can imagine, that would be a pretty spectacular sight. The reason these pyramids are shaped this way is so they represent sun rays. Imagine what that would have looked like when it was first built, with a shiny metallic top and smooth white finish on all of those sides. I think that would have been a sight to behold. Hey, I hope you enjoyed that video. I filmed it earlier this year when I was in Egypt. Now I'm currently in Melbourne, Australia, and tomorrow I am flying to the US. In fact, next week I'm actually doing a live show in Alabama with Henry from Minute Physics, Destin from Smarter Every Day, Brady Heron from Numberphile Periodic Videos and 60 Symbols, and CGP Grey from CGP Grey. Yes, he will actually be there in person. So if you want to come and join us, then check out the link in the doobly-doo. You know, on all of these long flights, I always need something to help me pass the time, and I know what I'm going to be doing tomorrow. I'll be listening to the brand new audiobook from Bill Nye. The book is called Undeniable: Evolution and the Science of Creation, and he actually narrates this book himself, so I can't wait to listen to it. And if you want, you can download this book for free by going to audible.com/Veritasium, or you can pick any other book of your choosing for a 1-month free trial. So I really want to thank Audible for their support. They've helped me go to all of these amazing places, and they have hundreds of thousands of audiobooks, so if you love audiobooks, then you should definitely try them out. So thank you for watching, and hopefully I will see you next week.
The law of inertia states that objects will maintain their state of motion unless acted on by an outside force. This means that moving objects will stay moving and still objects will stay still unless you push or pull on them. There are 2 safety devices in your car to protect you from the effects of inertia. The first is your seat belt. When the front end of your car rams another object, your car will suddenly stop or slow down. Because of inertia, your body will want to stay moving at whatever speed it was moving before the accident. If you're not wearing a seatbelt, this means you will hit a windshield. The seatbelt provides a force to stop your body's forward motion. The second safety device in your car is a headrest. When your car is hit from behind, the car is suddenly pushed forward. Your head will want to stay still, but your body will be pushed forward by the seat. This causes your head to feel like it is snapping back. Your head is actually staying still because of inertia, while the rest of your body is being pushed. Your headrest pushes your head forward with your body so that you don't suffer from whiplash. Look at the difference between a headrest that is properly set versus one that is set too low to push your still head forward.
Sir Isaac Newton. He came up with 3 laws of motion. We've talked about some of these before in previous episodes, and we're going to talk about his second law of motion. Now, second law of motion states that the strength of a force is equal to the amount of mass involved multiplied by any acceleration applied to it. That sounds a little complicated, but I have a simple demonstration to show you how this works. I have 2 objects. One is red and one is yellow, and that's neither here nor there, but this one is heavier, and you're gonna have to take my word for it. I've got something inside the red ball, which does make it a bit heavier, and there's nothing inside the yellow ball. So I have 2 different masses, a heavier one and a lighter one. And I draw your attention to our high-powered air cannons, which I have here on the stage. Now, what I'm gonna do is I'm gonna try and move these, accelerate these objects across the stage, using exactly the same amount of force. So I'm gonna put one of our objects, the heavier one, here, and our lighter object here. The force is going to be exactly the same behind each object. So I'd ask you, which one do you think would go faster and farther? Again, the force is the same, but our objects have different masses. If we look at that second law of motion, it says the strength of a force is equal to the amount of mass involved multiplied by the acceleration. I don't want to give anything away, but let's actually try this. Now, I've done something a little risky here, which is I'm pointing them at Parnelli, who delivers our programs here, has graciously accepted the job of tester for this. I've loaded him up, and we're going to fire these directly at Parnelli, and he's going to see which one is going to travel faster and farther. You okay with this? You're good? Good, because your contract says you're allowed to do this. So we're going to arm our system. We're going to put in some air pressure, so there's enough to, that should be more than enough. And we're going to do a quick countdown and fire these at our brave volunteer and see which one is going to travel faster and farther. All right, we're going to go 3, 2, 1, and could you tell which one was going faster and farther?
I had my eyes closed.
I did notice that you had your eyes closed, but I can tell you without a doubt the yellow one, the lighter one, was going faster and farther. So, what did we have? The yellow one. The yellow one went faster and farther than the red one because, of course, it's lighter. It takes less force to move something that's lighter. Now, not only do we see this in rockets, you want to have a nice light rocket to go into space, you actually see this in everyday life. With the price of gas going up, you'll notice people are trading in their heavy trucks for lighter cars because it takes less force to move that lighter object. So again, something that we're going to be seeing a lot more of. If that price of fuel keeps increasing, we want to try and find a really efficient way of moving ourselves around. For the Express here at the H.R. McMillan Space Center, I'm Cam Cronin. Thanks again, Parnelli.
Welcome to the European Space Agency, ESA. Newton came up with 3 laws of motion, laws that describe how forces and objects relate to each other. Hi Pedro, Alexander. We can see that they're floating. They're pushing against each other and move apart. That's an ISS battery and it looks heavy. That means it has a lot of mass, right? Once again, they're pushing against each other, but Alexander moves less. What we see this time is that for every action, there is an equal and opposite reaction. Newton's third law of motion. Alexander pushes against Pedro, action. This causes Pedro to move, reaction. At the same time, Pedro pushes against Alexander, action, causing Alexander to move in the opposite direction, reaction. And they moved an equal distance, action equal opposite reaction. The battery's mass is about 80 kilograms, so now the force is the same, but the mass is different. Remember Newton's second law of motion. Action and reaction are caused by the same forces, but they're expressed through different mass. Therefore, Alexander moves less. Let's see what the schools are up to. Here we go. This is like Pedro and Alexander on board the station. We add another girl and they don't travel as far. The force of throwing the ball makes her move backwards. A collision, that's a force. But do you know why only the guy in front moved? The students are arranged in what we call a Newton's cradle. Skater collides with the first student, action. The first student tries to move away from the skater, reaction, but can't, because there is another student in the way. So, the force of the impact is passed through the next student and onto the end of the line. Then there's nothing stopping the last student, so off he goes. This is like the guys on the ice, only the last ball moves. And here the two balls are moving, but they don't seem to go as fast. This is because the same force is travelling through the cradle, but is expressed through twice the mass. As mass and acceleration are related, the two balls travel less than the single ball. The third law helps us in other areas too. Space vehicles use it to lift off. The air or gas is heated up and forced from the exhaust, action, and the reaction pushes the rocket up into space. Now you know about Newton's three laws of motion. Law 1 states that objects at rest or in motion stay that way unless a force acts on them. Law 2 says that the force is related to mass and acceleration. And Law 3 says that every action has an equal and opposite reaction. But why should we learn about Newton's three laws of motion? Well, it's all about science and research. Let's ask someone who has been into space.
Bonjour, je suis Claudie.
Hello, I'm Claudie Eniere. I've been lucky enough to lead a fascinating life. First, I was a doctor, a rheumatologist. Then I had a chance to start a career as a scientific researcher in the field of neuroscience. And all that with the idea of one day being able to take part in experiments in the field of space research. I was lucky enough to be recruited as an astronaut, first by the French Space Agency, later by the European Space Agency. A career as a scientist will bring you a lot of happiness, a lot of learning and development. Most of all, being a scientist means paving the way for the future. It means being curious, helping each other to build today's world, to build the world of tomorrow.
There are a lot more questions one can ask. Why is everything weightless on the ISS? How does being weightless affect the human body? But for now, goodbye.